G'day everyone, welcome to Chem Explained. This week I'm going to talk to you about how to turn CO2 into jet fuel. For those of you with a very basic knowledge in chemistry, this is essentially jet fuel. This is octane, and this is used in both jet fuel and conventional gasoline that you put in your car. So when I say jet fuel, just think of our friend octane here. And it's called octane, by the way, because it has 8 carbon atoms surrounded by hydrogen atoms. We start off with CO2, which is reduced using hydrogen gas in the presence of an iron oxide catalyst to get carbon monoxide and water. And we see that carbon monoxide then moves over to a second catalyst, an iron carbide catalyst, where we then add more hydrogen gas and we get something called a methylene molecule. And the significance of the methylene molecule is it has 2 little arms, and that helps it basically chain together with other similar methylene molecules. Now this is pretty simple chemistry, and the equations make it look pretty easy, but there's actually a bit of a secret ingredient used in this process, which is the catalyst that I've just mentioned. These catalysts are a very, very small size, around 15 nanometers average size. And the reason they're this way is obviously because of a greater relative surface area, so there's more catalyst available to react with our carbon dioxide. And we also have 0.3 nanometer ridges here in the crystal structure. And the significance of that 0.3 nanometer gap is it actually allows carbon dioxide molecules to fit almost perfectly into this space and react, as you can see from the front view diagram. Now the other interesting thing we have here is the potassium and the manganese present in the crystal structure itself. And it doesn't actually change the structure, it's not put on top, it's actually integrated into the crystal lattice itself. And manganese and potassium that we use are actually what we call promoters. And what promoters do is they have many different functions in a catalyst, but in this case, the manganese increases the rate of reaction, and that's not too special, but the potassium on the other hand, it's the key ingredient that allows us to produce these nice long octane molecules. And the reason why it does that is actually because potassium has very low electronegativity. And carbon dioxide, although it's a relatively inert molecule, it's actually attracted to that lack of electronegativity. So potassium allows carbon dioxide to basically be sucked into these catalysts. Now the other thing that the potassium does is it reduces the chance of hydrogen gas from actually entering the catalyst. Instead of getting these very small methane molecules, which is just a carbon atom surrounded by hydrogen atoms, we actually, because we have less hydrogen in the system, we get more of these methylene molecules, so we get 2 less hydrogen atoms. And that allows them, like I said before, to chain together and produce these nice long molecules, very similar to octane here. Now, what researchers found was at the start of the experiment, they actually got quite a lot of these smaller molecules, but as the reaction progressed, the system began to prefer larger molecules to react with. The system actually preferred the production of larger molecules as the time went on. So it basically allows us to produce, with some sort of regularity, very large molecules, very pure fuel, which can be used to burn a lot cleaner than other regular gas that's refined from crude oil. The other thing is, it allows us to enter some sort of cycle where we combust gas, we capture the carbon dioxide, and we then regenerate it into usable fuel, compared to the normal, or the old-fashioned linear method that we're currently using of drilling up crude oil, refining it, transporting it, and burning it in whatever we need. So this development is pretty exciting, as it pretty much means that we'll soon be able to produce renewable fuels for cars and planes in the near future. We can use it as a resource rather than avoid making it in the first place, by trapping it right after leaving a combustion engine and quickly turning it back into something usable, or alternatively sucking the carbon dioxide directly out of the air. Make no mistake, this is likely the future of fuel and a big step forwards towards using fossil fuels in a more carbon neutral manner. That is, until battery technology is able to evolve to the point where it becomes usable in transport, such as long-haul jets and large ocean liners, which obviously need very small amounts of fuel with a very high energy density. And batteries at the moment just aren't up to scratch. So until then, this is going to be likely a very viable process in the future to reduce our overall CO2 emissions into the atmosphere.
Hey guys, thanks for making it to the end of the video. If you enjoyed it, make sure to leave a like and subscribe. It really means a lot to me. Also, leave a comment if there are any interesting new developments you want me to cover.